Welcome back, everybody, and welcome to this lecture where I'm going to try to guide you in what is the aim today. So I want to give you a reminder on the basics of the variational quantum eigensolver method. And then we are going to look at how we can simulate efficiently these Hamiltonians. And I'm going to focus a lot on this one-qubit system. So I hope you don't get offended if we stay with a one-qubit system, but that will prepare the ground for also next week when we go to the two-qubit. And finally, we're also going to introduce this Lipkin model, where one of the cases is going to be a four-qubit calculation. So I want to do this kind of baby stepping and building up the basic elements of the course. Just some information about where you find coding examples, because I'm going to use that example extensively today when we go through how we can use the VQE. We will also use the second half of the second lecture to more discuss where we are with respect to the project and do some hands-on. And we are going to look at the first, first step of the project, which is about the Bell states, and then how we can move into the simulation of the one-qubit system, and then how we can scale this up. So if you have the basic principles in the one-qubit system, it's pretty easy to see how you can scale it up to more particles. So the whole thing, as we discussed last time, is that we rewrite a Hamiltonian, or the quantity we want to calculate, in terms of Pauli X, Y, and Z matrices, or gates as we call them. And the final gate is the so-called identity gate, or just the identity matrix. So these are the basic quantities which we use to build up other more complicated systems with. And at the end, what you will see, like the Lipkin model, which we will discuss next week, we will end up with a four-qubit case, and then you will see a concatenation of X, Y, Z, and identity matrices. So that's the basic kind of recipe which we will use in order to perform simulations. And I wanted to give you a reminder of the VQE and then go through some technicalities. And then we're going to look at the codes. And then, as I said, the second half of the next lecture will be more hands-on, and Karen will also be here, and we will have more people to discuss with you guys. Just some kind of small technicalities before we move on. So one thing which I did was also to try to sketch a final plan before the Easter break. So the next week, we will introduce the final Hamiltonian, which is a famous model which has been used in many body physics for many, many years, which is called the Lipkin model. And some of you have met it already if you've taken a basic course in many body physics. And then we are going to look at how we can solve the eigenvalue problem for this Lipkin model. So the basic recipe, just so that you see the overarching picture, is you rewriting the Hamiltonian in terms of these different matrices, X, Y, Z, and the identity matrix. And then we have to see, the whole thing is about how do we make the measurement. And the measurement means often that we have a basis, which in our case is a basis of qubits 0 and qubits 1. That is our computational basis, which we use. That means that when we make measurements, we will often like to translate an X matrix or a Y matrix into a C matrix, because this basis is an eigenbasis of the C matrix. I'm going to repeat these things. So there will be some elements of repetition. I hope that's okay. And so that just to quickly remind you of some of the basic calculational elements. And then before the Easter break, which is Friday the 22nd, we will discuss this. We have a summary of the project, and then we'll start looking at other methods. And there's also the possibility, obviously, to come with inputs about things you would like to see in the second half of the semester. And that is why when you look here, you will see that there is a TBA to be announced. So I haven't decided on what we will do in the second half. So please, if you have something you would like to study or you would like us to discuss in the lectures, let me know. So one of the topics which we haven't discussed much is about quantum Fourier transforms, because they play a central role in many of the algorithms. So the focus now, before the Easter break, has been us calculating eigenvalues of quantum mechanical systems. So that's just one of the many applications. Okay, so another thing I wanted to say, if you look into the material which we have this week, and this is something which hopefully can help a little bit as a guidance for the project solution. If you dive into week 7, which is this week here, and you go to the Jupyter Notebook folder, you will see that there is a source folder, and that contains lots of functions where we set up the qubit basis, functions which perform the measurement with the C matrix, etc. So you can think of these as a kind of utility and background functions which are used in the code we will discuss today. Okay, so that's just some background information where you can find inspiration for you writing your own code. And feel free to reuse this material. Okay, so that was a little bit about technicalities. So let's just move into the topic for this week. And I want to do a quick reminder of what we did. And I'm going to use this one. So if you look at the material for this week, in addition to this article, which you also have access to in the articles folder on the GitHub address, the basics is actually to look at how we implement this VQE in an efficient way. This means that we need to touch a little bit upon gradient methods, which is something some of you who have taken a course which is called Computational Physics 2 have already met. So the variational quantum eigensolver, just to quickly remind you of some of the basics, that's a hybrid quantum classical algorithm. And one of the main applications is actually finding the ground state energy of a quantum mechanical system. And it has been very popular in simulations of systems from quantum chemistry. That means molecules, atoms, etc. And there are actually quite many applications of quantum mechanical systems from either nuclear physics, quantum chemistry, and also condensed matter physics. There's actually an algorithm which we will discuss, unless I get some other inputs, which is called the quantum phase estimation algorithm, which is based on the quantum Fourier algorithm. And that was the original proposal for finding the eigenvalues of a quantum mechanical system. So we will discuss that after the Easter break, unless we change a little bit gears and topics. And that algorithm leads to very long circuits and long simulations. So the VQE, being this kind of mix of a classical and a quantum algorithm, is the one which has gained the most traction when it comes to solving this type of problems. So it's normally more efficient, and we are in this noisy intermediate scale quantum era, which means that if the circuits become very long, then noise will become very, very important, and many of the calculations can just end up in just producing wrong results. So you can easily have thermal excitations in many of the candidate systems nowadays, which will spoil the computational basis for you. So there are some basic things here. Now, in the first part of the project, what we are dealing with is a one-qubit system. And then we don't need this identity matrix, but we could simply have an X matrix, a Z matrix, a Y matrix, and we could have something like an identity matrix. So what we want to do And this is the example which we will focus on mostly on today, is actually to calculate these expectation values. So this is not necessarily a one-qubit case, but this is a typical example of what you may end up doing. So when you see something like this, these are all tensor products. So the Pauli matrices are 2x2 matrices. This means that this could be the 2x2 identity matrix, and this could then be a 2-qubit example. So just to give you a typical example here, I'm going to leave some of this out, but I just want to remind you quickly about some technicalities. There is a lot of text there, which you can also read a little bit yourself. But just to quickly remind you, so one of the things we want to do, and as we discussed last time as well, is to rewrite the Hamiltonian in terms of an operator like the C matrix, the Pauli C matrix, which then, when it acts on the computational basis which we are chosen, shows you that this computational basis is an eigenbasis of this matrix. And you will see that when you then switch to x0 here, because that simply flips the states from 0 to 1 and from 1 to 0. So that means that this is no longer an eigenbasis of x, and you have the same thing for the Pauli Y matrix. Yeah. No, because if it's an eigenvector, then you have the same here times a constant. Yeah. Yeah, but you see, it's not an eigenvalue problem anymore. This is not an eigenbasis of x. Because else you would have 0 here and 0 here. Like you have here you have an eigenvalue +1, -1. But here you just have a value +1. I could have taken away +1 and just left 1 for the qubit 1. So that means that this is not an eigenbasis. So if you make a measurement and you use this as your basis to entangle states and make linear superpositions, when you make a measurement then we know that this will not project out 0, but would actually give us something different. So we would like then to reuse it or rewrite it. And one of the things which we did last week was actually to rewrite it in terms of 2 Hadamard gates. Now, what you see here is something which I wanted to emphasize a little bit, because this, since as we said last week, the matrix H, this Hadamard matrix, is a unitary matrix. So what we are doing here is to perform a unitary transformation of the C gate. This is essentially the general structure which we will use when we are going to rewrite the Hamiltonian. So we will try to find this type of unitary matrices. So when we come to the 2-qubit case, which is the next part of the project, then you will see that there will be combinations of these matrices. There will be a Z tensor product with a Z matrix. That can be rewritten just as a C matrix if I use something which is called the swap gate, which I will come back to a little bit later today. So there are, at the end, when you're rewriting your Hamiltonian, you end up with many of these, unitary transformations of operators, so that you can bring everything back into a set of operations, which then have the computational basis as an eigenbasis. Because when we perform a measurement, we are projecting out something. And then we discussed this as well, the Pauli Y matrix. This can be rewritten in terms of what's called the phase matrix. And we will see other examples later today of typical transformations. And next week, when we come to the Lipkin model, I will give you the kind of general expressions which allow you to set up the set of gates you need in order to simulate a more complicated system. So this is not, when I saw this the first time, I was thinking that quantum computing was something which would make my many-body physics easier. So I come from traditional many-body physics with the creation and annihilation operators and a lot of gymnastics with that. But then when I realized that everything is about you rewriting the original Hamiltonian in terms of chains of these Pauli X, Y, and Z matrices, and then to find the right one, which allows you to perform measurements, I felt a kind of, not exactly cheating, but I felt that the level of complication was not that different from what I was used to. That's a personal statement. And then what we also discussed last time were the rotation operators. So this is a little bit repetition of what we did last time. But I wanted to bring it up again because these are things which we need today when we are going to look at the simulations. So the whole thing with this variational quantum eigensolver is that we use what's called the Rayleigh-Ritz variational principle. And that simply states that for given Hamiltonian, the expectation value of a trial state, or just ansatz, puts a lower bound on the ground state energy. So if you have the exact solution, then you have the exact energy. Because then h times psi is just a constant times psi, and then you have a normalization constant divided with a normalization constant. In general, the guess you make will never give you the exact energy. Then the ansatz, which we discussed last time, that's chosen to be parameterized superposition of basis states that can be varied to improve the energy estimate. So we will make rotations on the Bloch sphere for this 1-qubit state. And these are the optimization parameters. And what we ended up with was actually to look at this. So I'm just going to move on a little bit here and then come back. So what we are going to do then is actually to replace a qubit, which we initialize as a qubit 0, with a rotation along the x and the y axis. But let me go back a little bit here. So what we're going to do then is actually to perform rotations along the x-axis and the y-axis. And one of the things is that applications of y rotations, they ensure that the coefficients normally remain real, which is not always what we want, but it's often satisfactory for many body systems. And when we've done that, when we perform these transformations, we will rewrite the Hamiltonian, as we said, in terms of Pauli strings, which is this P of I here. That P of I is either Pauli X, Pauli Y, Pauli Z, or the identity matrix. We perform these calculations, and then F of I is the expectation value of a given Pauli string. And what we typically do then is that we simply count the number of times if we have bit 0 and 1, and now we are looking at the 1-qubit example. So we would simply count the number of times we get n0 and n1, and then we can estimate this expectation value, which is then the expectation value of the Pauli Z matrix. And then we simply do this counting. And what we typically do then is that every Pauli string requires its own circuits. And what we would do then is when multiple measurement, typically each Pauli string requires its own circuit, where multiple measurement of each string is required. And to optimize, this is where the classical optimizer comes in. So if you had time to look into that article, what you would typically see is something like this. I hope you can see this well enough. Yeah, a little bit better. So this is the basic calculational scheme when you're dealing with the VQE method. So in yellow here, we have the quantum computing operations, and the blue ones are the typical classical elements. So one of the things which we are going to look at today is also the calculation of the derivative, the gradient. So what you would have, you have a given Hamiltonian, and then this is often rewritten in terms of second quantization. Then the Hamiltonians which we will look at are simpler Hamiltonians, which are already rewritten in terms of Pauli matrices. And that makes this mapping, which you see here, much easier. If you have a general Hamiltonian, this mapping can be a small nightmare itself. And you can get long chains of Pauli matrices. So that's the first thing you do. Now, what you would typically do then is initialize. So we can typically start with, for the 2-qubit state, we would start with qubit 0 and 0. That would be the initial state. And then, as you can see here, we perform operations on the given qubits. We can have, depending on the type of system, and as you may remember from some times ago, this would be a C0 or CX gate. This would be another gate. This is a new rotation. So you perform a set of such operations here. Then you perform a measurement. So you prepare to make the measurement. So not all of the parts of the Hamiltonian can be rewritten in terms of a Pauli C gate. So there will be a set of measurements of these Pauli strings, which you have here. Now, when you have this part here, this is the part which you then would feed into a classical gradient method. I'm coming back to that. And when you have that one, you update the parameters. With the updated parameters, you calculate the gradient. So this is simply what comes from Newton's method. So who has never heard of Newton's method? Yeah, okay, good. And I know that most of you have actually implemented either some quasi-Newton methods or just a plain gradient descent. So if you do a plain gradient descent, then this parameter alpha here is something which you would tune so that you get the correct answer. This is not the best recipe, as you will see later when we look at the codes here. So this typically what you would end up doing here is that you have some link to a classical gradient optimization method. So when you have then updated the parameters, you find then new angles to perform these rotations. You go back, you repeat the machinery, you perform the measurements, then you have new energies with new parameters. You feed these new energies back again, because then you have you can calculate again a new gradient that is fed into the algorithm here. And then you keep updating till you reach a convergence. That means that the gradient reaches 0, or as close to 0 as you define 0 to be. So that's a kind of basic overarching structure of the VQE algorithm. And you can break down the steps here. So let me just do that one. So what you would have then is an ansatz for the quantum state, which you would implement on a quantum computer in terms of these operations with Pauli matrices. Then the ansatz is measured in a given measurement basis. Then you do a post-processing on a classical computer, which converts the measurements to an expectation value. And then with this, you do a classical minimization, which is used to update the parameters. And then you continue like this. So that is the VQE, and it's a method which also gives you circuits which are not that long, and where the influence of noise, thermal excitations, and the environment in general, hopefully, is not that important. We don't know that before you run the calculations. So this is essentially the 4 steps, and we are just going to go through the codes now and look at how you can implement this properly. Okay, any questions? So this is still at the kind of overarching level without us going too much into the details. So one thing I wanted to say then is typically what we do then is that we would have a qubit is now represented as a vector where we have a rotation in general so that we can find a random 1 qubit on a block sphere. And then we need to tune these angles. So the before, typically, this is often the situation, you would have a qubit in just a 0 state. And that corresponds to the vertical position as we discussed last time. You could think of that as a qubit pointing to the North Pole in this block sphere. And then you will apply these operations here on this initial state. And then you have this angle theta and phi, which then are the parameters which we want to optimize. And the gates with the, we can actually set up 2 gates in terms of this will define 1 gate, and this is another gate. With 2 parameters will generate for us the trial wave functions. And that these parameters will be those which are in control of the classical computer and the optimization model. This, I'm just going to skip that one. So there's one thing I wanted to say a little bit about, and this is the simple example which we've been having. So let me just bring back the Jupyter notebook because now I want to use that one. So I will be switching a little bit between the Jupyter notebook and the slides. So let's just go down, scroll down a little bit. So this is the first example we have in the project. And in that case, we have this 2x2 matrix, which we then rewrote in terms of we use the computational basis, and we rewrote it in terms of the Pauli matrices. So I'm not going to go through this again because we've seen it many, many times. And essentially what we end up doing now is to run a calculation with some selected parameters. And then we want to implement the VQE algorithm to find the same eigenvalues. And when these are some specific parameters which we selected, I'm not going to discuss them again. And this is the eigenvalue which we typically get, 0.98 here. So what we did last week was then to rewrite this Hamiltonian in terms of Pauli matrices. So that was that step. And you can see now we have a Pauli X, Y, and Z matrix. And then we have the Hamiltonian rewritten in terms of this. So that's a simple case where we have a Hamiltonian in terms of the identity matrix. We don't have a Y matrix, we have a Z and an X matrix. And when we calculate the eigenvalues, we obviously get the same thing. And when we now look at this measurement, what we need to do here when we are setting up the code is actually to change the Hamiltonian. So what you have here is a kind of general Hamiltonian. I'm going to use the slides a little bit in the beginning here. So when you then look at a more general Hamiltonian, this is what we want to calculate. And we don't have a Y matrix in our case. And you can now see how you can think in terms of why we need to rewrite everything in terms of matrix, which has the computational basis as an eigenbasis. So the expectation value of this one is pretty trivial. And so that means that the expectation value here, the final one, is just this constant A. Now, when you now look at the Pauli matrices, so you can actually rerun this or calculate this with coefficients for different basis functions. So if you look at the wave function, we can now define. So I said that if you use the basis 0 and 1, that's an eigenbasis of the Pauli Z matrix. But I could now define the eigenvectors of the Pauli X and the eigenvectors of the Pauli Y matrix. So I could use that as my basis, right? So there's nothing which hinders me in using that as a computational basis, except that this computational basis is a little bit more complicated because it's already a superposition. So that means that if we are preparing an initial state, we would need to prepare an initial state which is a superposition of bit 0 and bit 1. That can often be difficult. So we would often prepare the system to be in one specific state. So if you then go back to the drawing which we had, if you look back at this general VQE algorithm, you would see now that it's pretty common to initialize it with a specific set of qubits. So we know exactly that, let's say particle 1 is in qubit 1, particle 2 in that one. Alternatively, all qubits are just in qubit 0. Okay? So if you look then at, there's nothing in principle mathematically which hinders us from choosing these spaces. And that means that this state here could then be a linear combination of 0 and 1. So you see the coefficients for the Z matrix, or it could be a linear combination of the plus and minus, which are these two states, or it could be a linear combination of the eigenstates of the Y matrix. Okay? So when you analyze this, when you perform these operations, this is typically what you get. So you get this coefficient, that's the expectation value of the poly Z, the poly X, and the poly Y. So when you use these inner products, the problem is that when you now look at them, is that they are the probabilities that after the C basis measurement is in 0 or 1. And then the quantum state psi will become either 0 or 1 when we make the measurement. So the problem which we have then is that if we now, suppose now we use this basis, then the type of measurement which we will end up with for the expectation value of Z is the counting of the number of times we have 0 and the number of times we have 1. And that means that these coefficients will simply be given by that. If I use the X basis, I would then have to make some kind of way to extract this information, which can be difficult because then I have another computational basis. So remember again that, I mean, theoretically we can do this, but experimentally you are locked to specific states which you want to use as your computational basis. So that could be the ground state of a system and the first excited state of the system. And when you have locked them, this is the basis you want to use throughout your experiments. The reason for this is also that these operations are often given by manipulations with lasers or magnetic fields, which means that they often target, the measurement itself targets these type of basis states. So this is a constraint which is not theoretical, but is actually constrained by the way we perform measurements in real life. So the difficulty comes from the fact that one may have the possibility to measure only in the C basis. And that's why we will end up with a series of transformations of basis states for the Hamiltonians which we have. So if you now look at the poly X matrix, what we saw last week is that if we use the Hadamard gate, which is this one, then we get this expression here. So that means that we would then rewrite the X gate. So if you look at a circuit with the X gate, and let's now just bring up the Jupyter notebook, no, the whiteboard. So if you look at the poly Z gate, so we would typically have a state, this is the one-qubit system. We would perform a rotation along the x-axis. So this is a gate. So it's a specific operation which we are doing. You can operate with this with lasers if you want to. That's the way you would do it experimentally. Theoretically, as we are in the lucky situation of being, we don't need any equipment. We can just do a matrix vector multiplication. So this will just be given by different poly matrices, which would then multiply our initial state. And then we would perform a measurement here, which is often written like this. And this is normally a Z gate. And that gives us a final state. And then we would just repeat these measurements again and again and again. And we would typically prepare the state in the same situation. Okay? Now, if you look at so this would be the way I would approach the expectation value of this quantity here. Now, if I then look at the X gate, what I need to do then, so I would have a qubit 0 entering here, and I would still perform these rotations, Rx, I would perform a new rotation, Ry, but since I have a computational basis, which is not an eigenbasis of the X, of the X matrix, I would have to perform a Hadamard transformation. I would perform a new one, a C here, and then a new Hadamard transformation, and then I would do my final measurement. So this would be the way we would set up the expectation value of the Pauli X matrix as a circuit. So I've never gotten used, I have to confess, I never gotten used to this kind of drawing circuits. I have this strange way of thinking of everything in terms of linear algebra. So it's that's the way I am wired. So I view this always as kind of matrix vector operations all the time. But this is the kind of way you typically see this represented in the literature. And it's a very intuitive way of looking at it. Okay, so that would be the typical way we would set this up when we just have a one-qubit system. And then you can do a similar thing for a Y-gate, but in our case, we don't have a Y-gate in the Hamiltonian. Now, the thing I wanted to say a little bit about before we move into coding is a little step ahead for next week. Because we have only dealt with the one-qubit system. But next week, we are going to introduce a two-qubit system, and we're also going to look at a four-qubit system. So that means that we will get chains of these operators. So if you look at this type of transformation here, what we have is that the X gate is given by a Hadamard matrix multiplied with the C matrix multiplied with a Hadamard matrix. Now, the Hadamard matrix is a unitary matrix. We know also that if I take it squared, this is equal to the identity matrix. Now, one of the things which we are going to generalize, yeah? You can do Y first and X afterwards. Could you say it again? I mean, this is because the cosine plus the Pauli X. So when you look at the matrix form, if we now go back to the, I think I have it. I think I wrote it. It's actually, if you look at the Pauli X matrix, or X of theta is then given by a cosine of theta half multiplied with the identity matrix. And then I have minus, and then I have I times sine of theta half multiplied with the X matrix. So that's the mathematical expression for it. Yeah, so when you run the VQE algorithm, what is pretty common then is to choose a random starting point. So you would just pick a random point on your block sphere, and then with that one, you would run your VQE algorithm. And you will see that right after the break when we look at the code here. Yeah, yeah. So what we do then, if we now look at the more general situation, when we have more qubits. So our general situation is going to be the following. So we will have, so this is P, uppercase P, is a string of Pauli matrices or the identity matrix. So this is now a string of Pauli X, Y, Z, and the identity matrix. So what you will then have is that this string here is now the tensor product of different matrices. So where this is now given by a tensor product, and you will often see this notation here, I equals 0 up to n minus 1. So the uppercase letter n is the number of qubits we have. And this P of I is one of these matrices here, or this one. So one of these. So this could be a Pauli X or Pauli Y. And these are all 2 by 2 matrices. So if we have 2 qubits, so n is the number of qubits. So that's a general expression. Yeah. Could you say it again? Could? Yeah. 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 Because if we now look at the next exercise, which we are going to deal with, so that means that the n equal 2 case, which we have in the project. So in that case, we have a 4 by 4 matrix, which we are going to solve. And then we have a Hamiltonian, which we are going to rewrite in the following form. So we will have a interaction piece, h of I, which is going to be given by a constant, hc. And then we have a Pauli Z matrix, tensor product with a Pauli Z matrix. So the first one is for qubit 1 and the other for qubit 2, plus a constant h of x, which then contains this part here. So this is an example of a string of such operators, or such matrices. What I have in addition to that is a part which is called H0. So let me just quickly remind you of that one. So this is just a diagonal part of that matrix. And I can rewrite that in terms of a constant, alpha I squared, which is just the identity matrix, plus a new parameter beta of I, tensor product with the Pauli Z, plus a parameter gamma of the Pauli Z tensor product with the unit matrix, I, identity matrix, plus a parameter delta with a tensor product of a Z matrix times a Z matrix. So this is my rewriting of the original Hamiltonian, which I have in the project, before we start with this Lipkin model. So if you look at this now, this is just a chain of Pauli X, Y, and Z, and the identity matrix. So the original problem which we had, the original as a Hamiltonian matrix, was given by some epsilon 0, 0, plus a interaction piece, h of z, and then we had 0, 0, and then we have an h of x, we had an h of x here, we have a 0 here, and we had a 0 and an h of x, an h of x here, and a 0. And then we had a diagonal here, which was epsilon 0, 1 minus this hc, and then we had epsilon 1, 0 plus hc, and then we had finally epsilon 1, 1 minus hc. So this is the matrix which we just, so this actually this was a little bit bad. Let me just try to be a little bit, write this a little bit better. So this should be 0 here, and it has 0 here, and this is the h of x. And that one, this, let me just rewrite it a little bit, 1, 0. I should have done the diagonals first. And then I have my h of x here, and we have 0 here. My drawing skills are not the best ones. Actually, the slides, everything is spelled out nicely in the slides. Okay, so this is, so what I did then, when I rewrote these parameters, I had this parameter alpha, which I can rewrite as this epsilon 0, 0, plus epsilon 0, 1, plus epsilon 1, 0. And you see when you do the arithmetics here, you will get back the results which we put up on the previous slide. This parameter beta is just epsilon 0, 0 minus epsilon 0, 1 plus epsilon 1, 0 minus epsilon 1, 1 divided by 4, and then gamma, and then epsilon 0, 0 plus, I think, no, minus epsilon 0, 1 minus epsilon, no, this should be plus, and then minus epsilon 1, 1. This is exciting, isn't it? delta, and this is epsilon 0, 0, minus epsilon 0, 1, minus epsilon 1, 0, plus epsilon 1, 1, divided by 4. And what we had is that this part of the Hamiltonian acting on 0, 0, that is a 2-qubit state, was given by epsilon 0, 0, 0, 1, etc. So this is something which we set up in the beginning. So you may say now that since this is a 4x4 matrix, which we diagonalize easily on any kind of under any kind of software, why do we complicate life this much? Because here, for this specific case, it's just a 4x4 matrix. But we are going to rewrite the Hamiltonian in terms of this string of Pauli matrices and the identity matrix, which means that in general, when we look at these expressions, what we have then is something where this string of Pauli operators, this string we put up, is going to be given by some unitary transformation. And this is transformed to a matrix where we can make the measurement. So when I put M here, this could be the Pauli C matrix. So this is the measurement type of matrix which we have. And then we have a new transformation. So just think of the Pauli X, which we wrote as a Hadamard, times a Z matrix, times an H. So this is the unitary transformation. And this is now the measurement matrix, so the measurement gate. So this is just an example. Now, things get a little bit more complicated when we are now setting up these different matrices. So if I take, and let me just anticipate a little bit that. So if I take this I, this is a 2x2 identity matrix, multiplied with the Z matrix, that has U as what is called the swap matrix, or the swap gate. We are coming back to this next week. So I'm just mentioning it now so that you can see how we are going to perform these transformations. And that swap gate is normally just written like this. Swap is equal to 1, 0, 0, 0. And then we have 0, 0, 1, 0, 0, 1, 0, 0, and 0, 0, 0, 1. So what this one does is that when it acts on 0, 1, it swaps it to 1, 0. It doesn't do anything on 0, 0, and 1, 1. So it just interchanges these 2 qubits, which could be in a kind of excited state. This is actually a very useful operation when you're setting up quantum computations. And we are going to have to rewrite our Hamiltonian in terms of these operations. So that will actually be a gate now, which acts on one of the qubits here. But we are coming back to that next week. So I'm just anticipating that when we get to more complicated and more qubits interacting, we will have to rewrite the qubits in terms of a set of operations, because when I perform this swap gate, when I do that, and you can see that easily when I take swap, and this is multiplied with the identity matrix with Z, and then I do the swap. So this is matrix-matrix multiplication. What you will get is actually 1, 0, 0, 0, 0, 1, 0, 0. Then I get 0, and then 0, and minus 1, and 0, and 0, 0, minus 1. So that when that performs the action on the states 0, 0, 0, 1, 1, 0, and 1, 1, you will see that that gives the correct eigenvalues. So we are coming back to that next week. I went a little bit over time, but I just wanted to give you the kind of overarching complications which we have to face. So I will give you the expressions for essentially all the Hamiltonians in terms of these chains of Pauli X, Pauli Y, poly-Z matrices so that you can actually implement them numerically afterwards. So after the break, we are going to set up the code for doing the for finding the eigenvalues for the 1-qubit system. And then next week, we are going to use the same machinery to do the 2-qubit and the 4-qubit case. And that's essentially what you need for the finalization of the project. Any questions so far? So the overarching philosophy is that we want to make measurements at the end. And that means we project out something. And then we want to perform this measurement in the computational basis. Okay, so what we are going to do now is to more look at the codes. And we're also going to look at the expressions which we can implement for the derivatives of the energy as a function of these parameters. And you could think of using something like a finite difference, but here we have actually an analytical expression for the derivative of the energy as a function of these rotation angles. So just remember now that the variational parameters are now these angles, theta and phi, which we have for the rotation matrix. And we are going to seed the system randomly with just a random position on the Bloch sphere. And then we are going to try to optimize the energy because we don't know if this seed, which we start with, is the one which minimizes the energy or not. So everything you will see now is partly a short repeat of what we had last time. So these are the rotations which we did. And last time we went through a very simple code. We didn't seed randomly the initial angles, but we did the rotations. We have the basic states, basis 0 and basis 1. And in the code, which we are going to see a little bit later, this has been made in a little bit more object-oriented way. So this is more brute force, just to show you the basics. And we have the new basis, we perform the rotation, and then we calculate the energy, as you can see here. And this is what we did last time. And the energy should be 0.98, and this is not very impressive. We then did a calculation where we run through a series of angles, and we just set up an array of angles from 0 to 180, and then we just performed these rotations here. And in that case, we saw that there was one case where we had a minimal value of the difference between the exact, so that means the absolute value of the real energies here, and the best value we got was something like 0.015. So this is not the way we will do it. There is a way to calculate the derivative of the energy. So if you look at what I did here was just to calculate the energy and then compare that one to the exact result which you see here. Now, what I'm going to do now is to calculate the gradients. And I'm going to use a gradient descent algorithm to find the best possible representation. So for those of you who have taken a course on machine learning, you're pretty familiar with gradient optimizations. For those of you who have done any course where gradient optimization is involved, it's essentially that the method which we plug in here. And we are going to use, at the end, libraries from scientific Python, which implement quasi-Newton methods like Broyden's method or Neal-Melder. There's Powell's method. There's a whole hierarchy of ways which allow you to avoid to calculate the second derivative. So keep in mind now that the gradient in Newton's method is the function we want to drive to 0. We want to have the roots of that. And that means we need the second derivative as a function of the parameters. So for those of you who are here taking the course on computational physics 2, you have seen the same thing applied to variational Monte Carlo calculations. So that's basically the same machinery. So I won't spend that much time on it because we have lots of lecture notes on that topic, and we are simply going to use it as a library here. So when we are setting up the gradients, you can use properties. I will abuse a little bit with the slides here. So what we need then, if we look at these rotation matrices, is that we can rewrite them like this. So this is just one of the sigma or the Pauli matrices. And then when we calculate the derivatives, we see that these derivatives of these matrices, because this is what we will have to take the derivative of to optimize the energy. So the energy is a function of these angles, which we are putting up here, theta and phi. And we want to optimize these angles. So we have a gradient for the energy, which is 0. And you can then, if we use derivatives of the Hamiltonian, and you calculate and you use the hermeticity, and this is just an example of you applying the chain rules and hermeticity, nothing more than that. So when you do that, you will find expressions in terms of these Pauli matrices, which look like this, plus the Hermitian conjugate. So we need to calculate when we calculate this quantity, what you can show is that, and in the derivations below here, you will see the full derivation of this quantity. So what you need to calculate, instead of using a finite difference expression where you just change slightly the angle, you can show that the derivative with respect to the parameters here are given by this expression here. So you just need to recalculate the energy for phi plus pi half and subtract phi minus pi half. That's what you need to do to calculate the derivatives. And what you have here is simply some block sphere mathematics, calculating the derivatives and rewriting the expressions. So when you do all these manipulations, you are ending up with the expression which you saw previously, this one here. So I just invite you to take a look at it. This is not the most exciting thing we do, but this allows us to have an analytical expression for the gradients, which is very important. So we have several notes on basic gradient descent, but when we now are computing with these gradients, so if you look at the code here, so this is now when I implement a plane gradient descent. So let's take a look at it. So this is the same code as before. And you see now I have my Pauli X, Pauli Y matrices. I have my initial Hamiltonian as before. I have the dimensionality of the system, 2 by 2. I set up the exact eigenvalues, which is the lowest eigenvalue I'm looking after. I initialize my system. So this is just my Pauli X and Pauli Y matrix, my original basis. I choose now to calculate. So the energy is simply now my basis and the conjugate transpose times the Hamiltonian times the basis. Here, I'm now picking a random value for the angles, for theta and phi. So I'm placing myself in a random position on the block sphere. Here, what I have now is the brute force gradient descent. If you go into the literature, and many of you have seen this because I know that you've taken a course on machine learning or you're taking computational physics too, which means that you have seen these calculations. So here I calculate the gradients. And this is the update of the functions where I now have a parameter eta, which functions as a learning rate for those of you who've taken a course in machine learning. It has other names in other types of applications. But if you are familiar with machine learning, you would recognize this as a parameter called the learning rate. And here, I have just done a very brute force way of setting up the number of iterations. There is no intelligent stopping. I just do 100 iterations. And I have a fixed value for eta. Now, the way you would do this is to use one of these quasi-Newton methods, calling scientific Python as a library, and then you would run the calculations with that. But if you now look at the calculations which I did here, so you see this is the exact one, and I'm getting pretty close. It's not that bad. However, I've been playing around before I came here, because if I put 0.01 here, you will not be that impressed. And now you see you have 2.65 here. So it's very sensitive to the learning rate. Yeah. 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 So what I'm exactly. So if I make it even smaller, then my search for the minimum may be even slower. I'll get another value. So you would have to play around like that, but this is not very efficient. So let me just quickly remind you of this kind of gradient methods. So what you would do is that you would set up a grid of these parameters if you don't want to use a quasi-Newton method. So this is just the simplest possible gradient descent. So you would set up a grid of values, and then you would pick the one which gives you gradients which almost vanish. So one of the tests you would put in here is whether the gradients vanish and whether the energy which you calculate doesn't change by a fixed amount which you have fixed. So the standard approach which is used if you don't want to calculate second derivatives, etc., then is to play around with the parameters. However, since this dimensionality of the problem is not that big, you don't have so many variational parameters, then we can try to attempt to calculate what's called the Hessian matrix. So let me quickly set that up for you. So let me remind you of that so that this doesn't come out as a bolt out of the blue. So when we look at these gradient methods, essentially what we are dealing with is a Taylor expansion of the energy around the optimal values, but we truncate the Taylor expansion at the level of the second derivative. So that means that what we want in this case, so the standard gradient methods, and in our case, what we would have is Newton's method, or Newton-Raphson, which is more correct. So if you have a function f of x, and you want to find the roots of that function, then you solve this iteratively. So that means that you would find the roots by an iterative process. So I'm not deriving it, I'm just setting up the final expressions. So this follows from you making a Taylor expansion. So this is for k. So this is a derivative. So this follows from Taylor expand this f of x around k plus 1, where this x of k plus 1 is given by some x of k plus some delta x. So making that Taylor expansion, and you truncate that at the level of the second derivative, then you can derive Newton's method. This is Newton's method for just one variable. You can generalize this to many variables, and then this first derivative will be the Jacobian matrix. Now, what we have in our case is not f of x. So f of x goes over to the gradient of the energy as a function of these parameters theta. That means that the second derivative, or the first derivative, is a second derivative in our case. So that means that if you look at our case, we are looking at the optimal values of the angle theta k, and this is given by the previous value. But now I'm going to have the gradient, and I need the second derivative. So I'm going to have 1 divided by the second derivative of the energy. And this is calculated at theta k multiplied with the gradient of E of theta k. So still for one variable, this could be done, but the derivative itself, this quantity, involves two function evaluations. If I take the derivative, the second derivative, I have suddenly 5 function evaluations, which I have to deal with. Furthermore, if I have more parameters, this becomes a matrix. And normally this is something you would find as a theta of k plus 1 is equal theta of k minus, and this is called a matrix H, which is called the Hessian matrix, which is now in our case the second derivative of the energy multiplied by this parameter here. So the simplest way you can solve this, simplest way is what is called gradient descent. And that means H minus 1 is just replaced by a constant. And you keep that fixed. That leads to what you normally call gradient descent. Yeah. Yeah. So that constant I call eta in the code, which I put to 0.1. So sometimes, or actually this is the general case when you do machine learning, because you have so many parameters, that it is cheaper to rerun it with different values of this parameter than to calculate the second derivatives for every iteration. But then, so this would be approach 1. But then, since we don't have that many parameters, then we have something which is called quasi-Newton methods. So quasi-Newton methods, there is a whole jungle of such methods. So we have Broyden's method, which is actually a modification of the second method. And then we have a Broyden, Fletcher, Goldberg, Shannon, Broyden, Fletcher, etc. There is Powell's method, there is Nelder-Mead, Powell, yeah, and tons of such methods. So when you look at SciPy optimize, you simply have to put in the acronyms for the different methods. And that means that these methods try to approximate the second derivative. And the way it's done normally, like Broyden's method, you start with the second, which means that you assume that the points can be interpolated with a straight line. That's the first simple ways of doing that. And then you have modifications of that. We are not going to cover that here. We are just going to use the libraries to optimize the function. And typically what we end up with doing then is to use one of these quasi-Newton methods. So this is just to give you the kind of overarching view on what we end up doing. So in my case here, I did a plain brute force calculation. And you see now this is just the implementation. I have 2 parameters. I need 2 gradients. I get 2 angles. And I simply keep updating and I play around with these parameters. And this accidentally gives me something which is pretty close. But I was actually playing around and around. And before the lecture, when I presented this the first time, I had forgotten about changing the learning rate to larger values. And I thought my program is just giving rubbish. And then I tuned the learning rate and then I got the right energy. This is actually what you end up doing if you do it the brute force way. But then there's a smarter way by which you can do that. And this was a code which was developed by a student who took this course last year. And I actually wanted to show you that as an example because he did a very nice job. So I wanted to say one thing about the coding. So we have this book by Robert Hunt, which presents a nice object-oriented platform. Feel free to use that, because you can actually access the GitHub site of Hunt and get all the codes which are there. If you want to follow what is set out there. Now, what you find here is just another way of setting up the basis. It's basically the same philosophy, but what you will see then is now the same thing. We are setting up the sigma X, sigma Y matrices. This is the Hamiltonian, which you've seen before now, ad nauseam. And we are setting up the different lambda values because we have a strength parameter in front of the Hamiltonian. So this just sets up the Hamiltonian, which we need, the matrix elements. And then this is just a plain diagonalization, which I've seen before. This is the exact solution by calling an eigenvalue solver. As you can see here, we just call linalg.eig and find the eigenvalues. Nothing special. So then we have the exact answer. Here, we prepare the state with the random values. So we have the sigma X, sigma Y. You recognize the Rx and the Ry matrices. And then we find the new state. Okay? This is the same as before. This is preparing a state. And I invite you to take a look at this folder, which we had here. So if you go to the course folder and you go to public and you look at the week 7, the Jupyter notebook, and then here you will find this file where you have the one-qubit class. You apply, set the state, initialize things, setting up the different Pauli matrices, Hadamard, this phase matrix, etc. No, so you find all these quantities. There is a measure function where we actually perform a measurement with a 0-1 qubit basis. There's a rotation here. So these are utility functions. There's a similar one for the 2-qubit class and for the 4-qubit class, which you need for the project. So whether you use Hunt's book or you feel inspired by this, just use them. So hopefully they can be they can serve as an inspiration for what you want to do. Then we do the energy. We set up angles. We have an initial state, so we prepare the state. We have a 1-qubit case in this specific case here. We have a measure set. And then we calculate the expectation values. So we have the expectation value C of X and Y, as we discussed before the break. And this returns expectation values. And here we are minimizing the energy. So we are running over a given number of iterations. And then we stop when the delta energy is smaller than 10 to the minus 4. That's where we stop. And you see now that we calculate the angles. We calculate the gradients and the plus and minus. So that is my gradient. And then I update the angles, learning rate times the gradients. And then I'm now setting up, calculate the energy, etc., etc. I run this 10,000 times. I start with a learning rate 0.3. So this is just a guess, which I feed in to the SciPy functions for the quasi-Newton method. So this is just a guess for the second derivative. And here I'm performing the runs, and you see now I'm using the optimize function here. So this is where I call the classical algorithm. So here I make the measurements, everything which you see here. If we now go back to that image we had before the break. So if we scroll up a little bit. So the first part you're seeing now is the one in yellow. So then I've done all the measurements, and then that is fed in to the classical algorithm, which does the parameter update with the gradient descent method. So if you scroll down then, and we go back to that. So let's do that. So the gradient method we are using is this function which you find here from SciPy. which is called minimize. And this calls a method which is called power. You can change that and you can use Broyden BFGS. That's another alternative. You can use Nelder-Mead, etc., etc. This finds the approximation to the second derivative without you calculating this matrix, which would be a 2x2 matrix, and then inverting it. And if you look then at the results, you can now see here, this is the brute force approach, which I had, and this is the one which SciPy gives you. And this is the exact result. And it does pretty well. So you will get results of similar quality. Yeah.
This is like methods for integration that you sometimes you just as an easy like trapeze.
Yeah.
And then you do something more advanced.
So when you use the Nelder-Mead method or the Powell method or these ones, what you're doing then is that you're approximating this second derivative by using first the second formula. That's the first approach, which means that you draw a straight line in the calculation of the second derivative. That's the starting point. And then you can improve upon that by making approximations to how you add to that approximation.
Well, there's no theory to which one is better.
No.
This trial and error.
So you would just trial and error. So many people use Broyden's method because it's pretty fast, but all these methods have their pros and cons. So in our case, since the dimensionalities are not that big either, basically I've tried all these methods. They give more or less the same result. The thing is that they avoid to calculate the second derivative. That's the quantity we don't want to calculate because that's time consuming. So you have an approximation to the second derivative. You can also do that in a brute force way by just fixing this learning rate and try to tune that one. There are many other methods. For those of you taking a course in machine learning, you know that one of the methods is called root mean square propagation, where you update the learning rate. You have adaptive gradients, etc., etc. There's a whole family of ways to update these learning rates. But this is essentially the kind of recipe which we would like to recommend. And next week, we will discuss the 2-qubit case and the 4-qubit case. And the complication then is simply that we have strings of Pauli X, Y, and Z matrices and the identity matrix, which become more complicated. And we have to map them so that we can perform measurements. So what we thought of doing now is that we wanted to discuss a little bit the exercises or the projects, and both Ruben and Karen and I will be here. So we can discuss a little bit and just figure out where you guys are, because it's the Easter break is just 4 weeks away. Time flies. Yeah.